Hello there, my name is Kevin. Today's power engineering discussion varies around the short circuit levels, normally called Ka in the electrical field. And we'll be discussing this in some detail so that people can actually then consider what we have to say in their daily life, dealing with short circuits and the levels and applications of circuit breakers, and just discussing a general topic in this discussion. We'll be going over things, where does it originate, why we need to be aware of it, multi-case circuit breakers and their Ka voltage relationship, very important. Cables and their Ka requirements, not generally discussed in great details, and prospective short circuit tests of the Ka and alternative sources. So this is a topic very close to my heart, but very misunderstood out in the electrical industry. And that's why we put it on today's topic. So let's have a look where where the Ka actually comes from. Where does it originate? So we know that for calculation purposes, in terms of certificate of compliance, the electrical system as such is connected back from the house or the business out into the road to a mini sub, to a substation. That substation has cables or overhead lines connected to somewhere, a grid. And the whole of South Africa is in fact connected to this grid system. The whole of South Africa, including things like power stations, everything is connected to that. And we can also then see that this grid in our calculations is set at 250 MVA, which is a sizable chunk of power. So by near and far, the biggest single contributor to the short circuit level being experienced downstream comes from that grid. And this is what I'll call this the general grid. You also get private networks, your generator, your photovoltaic, etc., where you have standalone systems. And then obviously the 250 MVA is not connected to that. So if you had a generator of a similar capacity to what the business or the house is, your calculations will be vastly different. In actual fact, it's the grid that really sets the short circuit levels because of the connection to that. Directly, there's a transformer outside of your house, outside of a business, maybe in the domestic type arrangement, there's a mini sub somewhere on the grid outside, somewhere in the road, somewhere in a corner. Older township areas might have a little transformer, might be in a little transformer house, may not be obvious in some areas. If we have a look at townhouse complexes, there could be a little power transformer area, grid network connected outside the main feed coming into that place. Generally speaking, the houses are more compact in those areas, and so the risk is that you need a slightly higher Ka than what you might have on the more traditional type township layouts where there's large distances in between. So let's have a quick check at what we're discussing here. Is obviously these power lines are all grid networked all over the country. You see them running up and down, connecting. And kind of we, from the non-technical side of life, nobody really cares about this type of thing. It's only the electrical guys who are fully aware of all this sort of system and the interconnectivity thereof. So we've got little houses, our normal houses connected up to a little transformer, down to the streets, down to a distribution area. This might be at anything up to between 11 and 66 kV, depending on the area you're in. And then eventually these travel right around the country, and there's a huge grid network in South Africa, as indeed most countries have that type of thing. And then a power station, hopefully a running power station connected to it. And in fact, many power stations grid networked into that. So this is kind of the source of the power. Now, a short circuit condition will occur if two phases touch. or a phase goes to ground, ground being in South Africa and many countries, a star-pointed ground and earth and neutral all in one, so that if any phase touches ground and any phase touches each other, there is a dramatic short circuit available. And that power is basically determined by things like if there was just a straight arc, an arc resistance, a resistive base, and there is a theoretical maximum that will be obtained with as low or as negative value short resistance in that equation. Circuit breakers obviously need to handle these type of things. That's what their whole application is. They, on higher level short circuits, need to disconnect that very quickly. It's important for their longevity. Circuit breakers only have a fairly defined short circuit performance starting at twice a fuse, so in other words 2 trips at maximum value, and going up many dozens of times if that short is of a muted level. In other words, it's not as high as discussed. So this is the background of all the connections that we have, and this is fundamentally why the short circuit exists. Effectively, a short circuit, wherever it's applied, let's say, and we're talking more on the contractor level here, we are talking about at the house, at a factory, at a business, a commercial type arrangement, and that's the risk that you have of the short circuit. And that short circuit has a defined maximum, and it's very important to discuss why that's important in the application of the equipment that is used in and on that level. So why do we need to be aware of this type of thing? And of course, like we've alluded to, there are short circuits between any phase and phase, phase and earth, and phase and neutral. And there are tremendous forces. So these forces are obviously things like mechanical forces, and the risk of fire with short circuits and arc fires occurring. And if they're not disconnected in time, they could have a huge material effect, fires, businesses burning down, houses burning down, etc. So we need to understand that the circuit breakers which are selected in these environments need to be correctly selected. Now, most of what we see in the market are simple things like little molded cases. You buy what you buy. It's thin, it's a CBI type rail, it's a Fuchs breaker, it's a brand that does that. And of course, without thinking, people just apply those things. But when things like CFCs are signed off and there's a qualification on that environment, which sort of says, is this a safe environment? You need to be able to confirm and prove that that statement is in fact true. We also can't generate a huge short circuit, damage the circuit breaker, put it back into service again, because the life of that circuit breaker could be killed. It would be kind of jumping out of an aircraft with a parachute that opens, and that parachute size is sized because of the weight of the thing falling with it. And then if you were using too small, it would crash into the ground. So we need to do these type of tests. You can't actually do a physical, you could do a physical test and prove and disprove anything, but it's basically a destructive thing, you throw it away. You wouldn't prove your car airbag would deploy and your face doesn't get smacked up against the windscreen, and you wouldn't have much car left at the end. So these things have to be done in such a way that the actual, how can I say, the actual test is done in a non-invasive way that still leaves something there at the end. So on the screen, as you can see, I've pulled up a circuit breaker. Let's get a bit of a closer look at that. We can see this particular brand of circuit breaker, one of the CBI's K50Ds, has a label on. So how do we know from a circuit breaker that we're going to apply what is on there? And of course, some of the problems that we have is that The circuit breaker is quite a variable thing. So if we have a look at this particular one, we can see there at 690 volt, it's rated at 8 kA. Up to 500 volt, 35 kA. 460, 50 kA. 380, 65. 250 volt to 20 volt, 75 kA. And if you just look here, you can see that the 500 volt is a DC rating of 20 kA. Also on the front here, it says 50, 60 hertz, giving us some idea that it doesn't really matter what hertz. Obviously, South Africa is a 50 hertz environment. America and certain of their allied states would be 60 hertz. And for the sake of a circuit breaker, you can see that it doesn't really matter what Ka we have. That is all of the same thing. There's no difference on the actual frequency that the power supply would be. You can see here that's IEC 60947 part 2, one of the world's biggest specifications in terms of circuit breakers. We also see at the top here, it's a 400 amp frame size. So this particular breaker could be anything up to 400 amps, 3-pole. You do get 4-pole, but you get 3-pole in this case. And ICS equal ICU. Now this in itself needs to be a little bit explained. ICS is typically all these service type level arrangements, which are slightly more than ICU. So normally speaking in the electrical industry, we are talking about ICU, the ultimate braking capacity, ultimate being 2 operational type of thing. So this particular breaker will be tested at 8 kA. It will trip. It will be closed back into that short circuit, an 8,000 amp short circuit. It will trip, and it's very much toast thereafter. It's going to pass some rudimentary tests, typically something like the 8 kA test is going to be a trip afterwards of something like 200%. It's going to get pretty warm. It's really just survived. It can survive slightly better. It can survive that, but that's the test. It's put up to a routine of tests after that. ICS is a service level, so it's another round of sort of tripping that you can have. And most products these days are pretty much equal to. In the past, a breaker could be anything, and it could be rated as such that it's 50%, or it's 80%, or 75%, or 90%, or whatever the value is. That means if you tripped it more frequently, you would have to lower the Ka in order for it to survive. So if we have a look at a 415 grid network, which is kind of what we have in South Africa, this product is a 50 Ka. And we need to have a look here as well, because the grid network in South Africa is not actually 380 volt, although we might measure 380 volt for a lot of it. It is a 400 volt network. So we are talking about a 50 Ka network on this particular breaker. And it's very important to discuss this, because what does this really mean? It means if we have a circuit, short circuit level available at a certain level in a panel board, and it is, in this case, 52 Ka, you can see here that you cannot put this breaker because it's a 50 Ka. It is underrated in terms of that. However, if you only had 35 Ka in that same panel board, and we talk about 400 volt networks there, the 50 Ka would be fine. You can overvalue that. Obviously, the performance is that. Now, look, there's a lot of details in terms of circuit breakers that we've skipped through here. There are some basic courses that if you really want to know more about circuit breakers per se, what they do, what they don't do, they are not miracle devices. They very often in the industry, people think that, a fuse blows once. If you have a short circuit, you go and replace it. If a circuit breaker has done many trips, and I'm talking about a number of high-level trips, and it breaks, they think it's a faulty circuit breaker. They're sent it back to the manufacturer claiming your breaker doesn't work. It's not going to work forever. It has a pretty much defined life. And that life is, if you take ICU at, say, in this case, 50 Ka at the 415 level, it's going to do 2 operations, trip close, replace, trip, plug, and that's it. It obviously has some survivable tests that they must do at the end just to be able to qualify that the unit passed, but that's effectively that product gone. At your earliest convenience, you need to replace it. The reality is that in our houses, for instance, we might in 20 years have 20, 30, 50, 60, 100 operations and the breaker doesn't break. So why would that last so long? And that's lasting so long because the prospective short circuit of these specific faults that are being experienced are far, far less than, you know, what we have from a breaker design perspective. All right, so this course isn't really about circuit breakers per se, so but there's a number of things which we need to understand from the circuit breaker when we apply it in this realm of what is happening with the KA. So observations, as we could see on there, the KA on the circuit breaker, it's linked to a specific voltage. So you can't say this breaker is 50 KA and it's over every voltage that you can consider. You can see that there's a general downscale in value as the voltage of the network goes up. That is not consistent between brands and models, etc. You might find at 690 that you get down to as low as 8 KA, as we saw there. Or maybe a product isn't even rated for anything over 600 volts. So some of the products you measure, some of the technologies that we could see there, there is a DC voltage mentioned, which is used for maybe batteries and that application. And for circuit breakers, special consideration needs to be taken when you apply DC on these. They need to be connected in certain format ways. You need to understand that DC being a positive and a negative only, on the three-phase breaker, you need to be able to wire it in a certain way. As you can see, the DC KA is actually quite low relatively. So by reasoning, we can see that the DC is quite damaging to a circuit breaker compared. And of course, some circuit breakers may not have DC qualification whatsoever. And on others, you might have only DC breakers where they've not been qualified for AC. So we had a look there and we said that ICU is the ultimate two-shot level. That is normally what everybody talks about when we're talking of KA. We don't normally talk of service unless we are qualifying it. When we have a look at it from a consultancy type value where it's being specified. So yeah, we could say that an ICS equal 100% ICU is probably a breaker that is better service life than one of the older level types, which was 50, 75, 80, or maybe even 100. It really means, of course, that that circuit breaker has been tested to those levels and approved very often by a third-party approval, a SABS testing house, a SANUS accredited test station, some or other third-party benefit party that has qualified it. We should not exceed the KAs, as we said, either in voltage or KA. So if it's a 415, 460 volt, and we're putting it on a 400 grid, that's also fine. If it's below the 50 KA, that's also okay. And as we said, we can utilize it if it is above, because our calculations will give us all sorts of values, and you will see that circuit breakers are generally specified by the manufacturers in something like 15, 20 KA, 25, 30, 35 KA. They go up in steps. So as long as you're below that, we are fine. What is not always in this consideration is, of course, the cables and the KA requirements. Now, this is not really of much issue when it comes to the type of stuff we have in a domestic environment. This is really where you need to have a look at if you're signing off boards in a large installation, typically a large industrial type environment. We must understand that when we talk of the KA and availability, and in like a domestic environment that's measured at the panel board, And in typical fashion, it will be measured at the dB board in a large industrial sort of complex. So the short circuit is going to be carried by all conductors from the grid down to wherever the short is. And that application is generally considered to be south or the load side of a circuit breaker. That indicates that there's an element of risk to things like on the line side of the circuit breaker, typically your bus bars or your bus bar feeder, your droppers, all those type of things are also subject to that same short circuit. And probably the worst case that we can consider here is if you had a large panel board and you only had a small tap off, less than 5 amp type of feed to some equipment, voltage measuring devices, some electronic control relays or something in that line, where you're only looking at 5 amps and you're going to connect to, say, 30 Ka bus bars. I mean, you need to understand that the cable connecting there is going to be sized not only with consideration of the ampage, but needs to be sized in accordance to what the Ka availability is on there. So if your bus bar supports are, let's say 30 Ka, and that's a panel board that's designed for 30 Ka, and you're going to take 5 amps off that, the cables connecting from the bus bar down to that control equipment, whether it be a circuit breaker or a fuse, are going to suffer 30 Ka. And of course, at 5 amps, you could immediately go and say, well, that's 1.5, even less maybe, squared millimeter cable connected to that. That would be the wrong approach. And that is kind of what I'm alluding to with this slide. The circuit breaker can trip and protect the cable, but the physical forces available on that cable could rip itself completely out of the terminations. The mechanical forces on that cable will be so extreme at a short circuit level of the 30K, it will rip itself to pieces. So it's not really going to, it could even fuse, I suppose. But the whole idea here is that cable down to the protection level going out to the load, in other words, the 5 amp load, that is the protected zone that needs to be adequately catered for mechanical short circuit levels. So that would mean that instead of having a 5 amp cable choice, you'd have to choose it much higher, and you'd have to brace those cables. So the other thing that you don't see really in little domestic boards is that the cables themselves are generally just wound or coiled or laid or put in their side, and that they're not bound in any way. Whereas when we get to large panel boards, that sort of support becomes extremely important. So things like behind the circuit breaker, behind the ACB, you need to have a look for things like, are those cables themselves supported against the mechanical forces likely to be applied on there, that they don't bend, warp, and cause secondary type damage. In other words, like a 1.5 mil cable might just pull itself free, flay around inside the panel, and cause an almighty short circuit, damaging the whole thing with a simple couple of hundred or a couple of thousand amp short circuits being applied to it. So it's very important to also look at it. Generally speaking, panel boards which are built by reputable companies and are type tested panels, they are taking care of that without anybody really worrying about it, because that is their line of business and that is what they do for a living. And if they type tested panel boards, they have to be set a certain way to achieve that type test, much the same way that circuit breakers are tested. Panel boards over 10 Ka is really where the risk is, and they should all, by our wiring codes, be type test panels. All right, so let's have a look at, okay, so we need to be able to establish a Ka prospective short circuit level at the panel boards that we're busy testing. So there's a number of ways that we can have a look at this and check on that type of thing. How do we generally get it? So we can do a prospective short circuit test. So there's fairly expensive equipment out there that can check to see, without causing product damage, what the level of short circuit is. And that's by applying a very short circuit with a defined impeding value, defined resistance, and doing that very quickly and doing the measurement. And of course, as guys doing CFCs, you've got to have the equipment to do that. You need to be able to establish exactly what it is. Other ways of doing it, of course, and on some of the test equipment, it's not available to do 525 or 1000 volt in the mines, for instance. You could have the suppliers giving you a requirement and saying, well, I'll give you XYZ kVA transformer, and you can have it indicated on a wiring pattern or a consultant wiring diagram to indicate what you need to put there and to ensure that that's there. You might indicate this is a 10 kA short circuit level panel with 10 kA buzz bars there. And those short circuits which are there for short circuit capability are generally designed around 1 or 3 second activity. So it's relatively a long time, and it can cause lots of damage over that period of time. We could really look at existing equipment. I mean, if you're going to a domestic house and everything looks right, and the minimum is in terms of those 2.5 or 3 kA, depending which spec you're looking at, and you replace it with that, the risk can't be that much worse than what it is. I think in today's modern areas where I would be more worried is some of the townhouse complexes, which generally could be above the older levels of that. And of course, like in a normal house, in a more traditional township environment, they don't really even get 2.5 or 3 k's. You do the measurements, you're probably getting somewhere between, I don't know, 700 amps to 1.2 maybe if you get that high. And so you can't really go too much wrong with that. And if the existing equipment's there and you just want to replace a breaker, you don't really have to go out of your way too much on replacement level for the odd breaker. Some of the companies provide tables. Of course, some of the guys do have tables where you have a transformer level, a voltage. Firstly, we need the voltage to establish. Then you look at the kVA of the transformer. And the guys have worked on average values. So they've said a transformer normally in this class is between blah, 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 A and B. And this is the tradition. It averages on that level. They do the calculation in KA. They give you cable sizes. So one of the things about the KA is the further away from the transformer and the grid you get, the higher or the lower, the higher the resistance is, and therefore the lower the current is. So that's a very, very vital thing to understand. In other words, if you're sitting 400 meters from a transformer of X kVA and you're sitting at 10 meters from that, there's going to be a serious difference in the Ka level that you need to apply. So it's an important thing to understand. And some of the guys have nice tables for that type of thing. CBI, for instance, has a list of tables, a couple more calculations on there. So you can very quickly just have a quick scan on that thing and decide you're 40 meters away, you have a 25 millimeter squared cable, and your Ka will be 18 and the breaker you've got in your hand is 25, so that would be fine. So that type of thing solves a lot of that, especially if you know the transformer size you're dealing with. On many plants, you have a sizable mechanical and electrical team, and those guys generally know what's there. Sometimes in a township area, you know what a transformer is, you can get access to that. More closed places, you don't have access to that. But a mini sub, for instance, often has a label on the outside, so you can kind of see what is there. Mechanical strength on cables, just we've probably skimmed over, this should have been the other slide. In terms of the actual Ka withstand, is approximately the square millimeter withstand level. So 25 millimeter square cable, sorry, is around about 25 Ka. So as I mentioned, the 1.5 squared would be a waste of time with a 30K short circuit. And of course, you can do the calculations. Nothing stops you using calculations from first principle. Could be wasteful in many terms because, you know, these things don't change. The only things that do change, of course, is voltage, but it should be a grid network. So we've always termed that as consistent. The transformers themselves may have actual VA and other values which change, like your empiric value might change. Sorry. So if the empiric value goes below the average, you can expect the Ka to go slightly higher. If, of course, the voltage goes on the lower side, that will also then lower the Ka. So it does vary quite considerably, and we need to understand where that is in terms of what we need to apply here. So just to recover then, or reiterate what we said, it's important to find out why and what Ka we have on those sites. There's a number of ways of doing it. We need to understand how we determine that on the particular circuit breaker. Hopefully the circuit breaker has a label on there. It shouldn't be confusing if you know what you're looking at and the voltage of the network. So very important in terms of how we get to that arrangement. And where we go in terms of the application and signing off. So in hindsight, Ka is not something that should be feared as long as you understand what is going on with that. It should be quite okay. And if you apply it in a rational and determined manner, as long as you understand what you're doing, it's done in the correct fashion. You should be able to, you know, do the right thing.